Hi, so this is our video for our last procedure dealing with proportions, means, confidence intervals, and tests. This is a two-sample t-test to assess a claim about a difference in two means, so mu sub 1 minus mu sub 2. The question we had from our IQ test is one gender smarter than the other? So comparing our two groups again, I still have list 1 as my males and list 2 as my females. State and plan identifying the name of the procedure. So, two sample T hypothesis test to assess that difference. The hypotheses I've already written in, so you can do it one of two ways. Typically, it's the first one that's written, that the mean of the males equals the mean of the females for the null hypothesis, which means there's no difference. So if there's no difference, when you subtract, you would end up with 0, which is the second way to write it. The alternative, because we just wondered, is one smarter than the other? Didn't have an inkling as to which one was the smarter of the two, so that we would do a one-sided if we thought males were smarter or females were smarter. So here we're just looking at, is there a difference or not? And so not equal to is the sign that I need to use in my alternative. And again, either the mean of the males does not equal the mean of the females, or their difference does not equal 0. These conditions I included in here, but they are the same as what we did for the confidence interval to estimate the difference in those two means. I just spaced it out a little bit for you and reformatted. So random, again, checking that it's for both. Independent, checking that 10%, and that they're reasonably independent from one another. And then the normal condition is where we really get down to business here. Since both of our samples were less than 30, neither is greater than 30, we're unable to apply the oh so helpful central limit theorem. So when you're given the data, you can check the condition with one of these three graphs, the box plot, histogram, or normal probability plot. If you are not given the data, then we have to, if we're told anything about the shape of either population, use that information, or we have to just assume that we don't have outliers or skewness, or if we're not given the data and it's because we have more than 30, we can just say that the central limit theorem applies. So no matter the shape of each of those populations, that sampling distribution of the differences is going to be approximately normal. So these, again, we checked males and females. No issues with the males. The females had a little bit of left skew. We could say proceed with caution. The procedure can handle the little bit of skewness that's here. It's not a very small sample size. We were like mid-20s, 25 and 29, I think, for our two samples. So it's not terribly non-normal. I didn't say proceed with caution, but you do have the option to do so. So for the do step, I'll again write out my work. Okay, so for my test, I have my test statistic T equal to the difference in the means, males minus females, minus the difference in the true mean of males minus females, which we typically just write as 0. That's from the null hypothesis. I remember one number 6 where they gave us a value where the difference was something besides 0. So you can just expect it to be 0. And then the square root of, and this again goes all the way back to our chapter 6 in combining these values, since we are not able to add standard deviations, but we add variances, and then we can square root to get back to standard deviation. So S squared for the males, which is the variance of the sample for the males divided by that sample size. And then same thing for the females. Now, you do not have to fill this out. You could enter these values just into the formula without everything listed in notation. It's really difficult to keep track of those subscripts and the bars and the exponents. So if you had just named the test up above, that's enough for identifying the procedure. So from here, the calculator is the best bet. Okay, so again, recognizing that formula, I then hopped over to my calculator to enter all of this. I still have my data typed into lists 1 and 2. The 2 sample t-test, if you go to stat and over to the test menu, this is the fourth option, lists 1 and 2. My alternative is not equal to. We don't pull them. That's assuming that the standard deviations of the populations are equal, and there's no way that we know that much about the population to assume such a crazy thing. So that's always no. And then I went to calculate again. The draw feature would give you the bell curve and shade both tails for us. So the results are the screen capture on the right-hand side where we are reminded that we entered not equal to for our alternative. Our test statistic from the formula up above, negative 1.314, not that far away. So a p-value of about 0.195. And so each tail had almost 10% area in it. We did, when we did the confidence interval for this, recognize that because 0 was contained in the interval, that we are unable to conclude that there is a difference. So this is just reinforcing that. The degrees of freedom, remember, need to be listed in the do step all the time as well. So our conclusion would be that we do not have enough evidence to reject the null hypothesis at really any reasonable significance level. And by that, I would mean even 0.01, we don't have enough evidence. 0.05 is our typical, and then 0.01. Sorry, I think I said 0.01, 0.10, 0.05, or 0.01. As our p-value is greater than all of these levels. If the true mean IQ test score were equal for males and females, we would see a difference as large as ours, about 19 points, we'll call it 47% of the time by chance alone. So they were a little bit different, not that different, and you can see there the scores of 5.9655 on the computer output and 6.44. So only about a half a point on each one. So again, identifying the test by name is definitely easier than formula. Stating the hypotheses, checking the 3 conditions, showing the work, including the degrees of freedom. And again, the calculator is just so much easier for this because you can get exactly what the p-value is as opposed to using table B. And then your conclusion needs to make a decision. So we said we don't have enough evidence to reject the null hypothesis, or you could say you failed to reject the null hypothesis. Linking it to the alpha level, our p-value is greater than all of those. And then having everything in context will earn us full credit on a 2-sample t-test to assess that difference in means.